The premise of this presentation is that, apart from matter and energy, entropy depends on universal expansion, and although locally it's constantly increasing, cosmically it's constantly decreasing, heading toward zero. As usual, this slide allows the reader the option to skip what is already known or at least believed. Again, I do not recommend bypassing any slides since it's a small presentation anyway. We believe that entropy or disorder is created whenever energy meets matter. Discounting the effect of matter for the moment, since entropy depends on energy, I need to define energy. And energy has several definitions depending on how it's used or needed. But most of these definitions and transformations are actually based on the interaction between energy and matter. Today, the purest form of energy is the energy released by stars and other astronomical entities. Regardless of how it's created, we call this electromagnetic energy. If electromagnetic energy encounters opaque matter, it can be absorbed, and in the process, atoms and molecules speed up. Now we call this heat energy. If it encounters a photocell, it kicks out the electrons in the photocell, and we call this electrical energy. If it falls on a leaf, it forms new bonds between atoms and molecules, and we call this stored chemical energy. When electromagnetic energy from the sun impacts the air, it allows air masses to rise, and we call it wind energy. Whenever energy is bound to matter, it can be converted into other forms of energy. For example, in a power plant, chemical energy from coal is converted to heat energy, and then heat is converted to electrical energy. When breaking up water into oxygen and hydrogen, a process called electrolysis, electrical energy is converted to chemical energy. The internal combustion engine changes chemical energy from gasoline to mechanical energy and heat. Some of these transformations are irreversible. Heat from a car engine just dissipates. But the final form of energy is always infrared or electromagnetic energy, which expands into space at light speed. With the exception of electromagnetic energy, all these forms of energy depend on matter. So I'd like to propose a narrower definition of energy, one that doesn't include matter. I'd like to define energy as a disturbance of space or a disturbance of space carried along by universal expansion at light speed, which I believe is how fast the universe is expanding. In this definition, energy can be carried through space that's occupied by matter, but while transiting this space, energy is absorbed by matter, which accelerate the particles that make up matter. The accelerated particles then re-radiate most of their energy at a low frequency, but still a disturbance in space or of space. And universal expansion again carries this radiation at light speed, but at a longer wavelength. Between absorption and re-radiation, there's a short time lag, which takes us to the second law of thermodynamics. Just like energy, this law has several definitions depending on where it's used and what's it trying to explain. In terms of heat energy, we say that heat flows always from hot to cold. It says that not all heat can be converted to work, and whenever there's a difference in temperature, motive power can be produced, and entropy always increases. But this law also applies to other situations. It applies to the fact that energy always seeks its lowest point, and natural processes are irreversible unless energy is used. But at its most basic level, the statement reduces to the idea that energy cannot be contained. Energy has to move. The question is, Why does it have to move? What is the motive force behind this compulsion? Anyway, even though energy has to move, this doesn't mean it can be temporarily stored, like electricity in a capacitor or chemical energy in a bottle or potential energy in the spring. But if stored for a long time, a capacitor will discharge, chemicals will decay, and a spring will deform permanently, which is the slow release of energy. And once that energy is released, it must expand in three dimensions unless it's recaptured. So, what exactly is entropy, and what does it have to do with the second law of thermodynamics? Let's return to the previous idea of electromagnetic energy encountering a dust cloud in space. When energy impacts that cloud, dust particles absorb the energy and accelerate in random directions. And we know that because energy accelerates matter. After a brief time, energy is re radiated and it exits that cloud, continuing its travel at the speed of light. But because of its loss, the energy wavelength is lengthened. That's the second law of thermodynamics. Energy cannot be contained. Some energy is moving with dust particles, the rest escapes as infrared or other form of electromagnetic radiation. Here we also have a solution to the problem of why energy must move at light speed. It is carried by universal expansion, and that's how fast the universe expands. The universal expansion carries electromagnetic energy at the speed of light, but it can't change the velocity or direction of moving masses. That's inertia, Newton's first law. Objects in motion must maintain the same velocity and direction. But inertia is an undefined given. There's no reason given for it. Now, every substance has a coefficient of heat conduction called the substance thermal conductivity, which defines how efficiently heat energy is transmitted through the substance. This idea of conductivity applies to electromagnetic energy also. While inside a cloud, the effective speed of electromagnetic energy is reduced. But once outside the cloud, electromagnetic energy is carried by universal expansion again at light speed. And as I said, universal expansion can't change the dust velocity or direction, but it carries those particles already accelerated by the electromagnetic energy at whatever velocity and direction they were accelerated at. That's why entropy is defined as disorder. Energy accelerates matter in all directions, and universal expansion keeps that velocity and direction going. Simply stated, matter interferes with the motion of energy. So let's explore why heat can only flow from high to low temperature. The total thermal energy, heat, of a system depends on how fast its components are vibrating and the quantity of matter in the system. More matter means more heat, faster vibration means more heat. In the previous slide, I said that universal expansion keeps matter moving at whatever velocity it has. Adding energy to a system accelerates the components' motion. Afterwards, universal expansion keeps those components moving at whatever velocity energy gave to it. So if two systems are in contact with each other, the particles that are carried at a faster rate will be carried into the slower moving system, giving us the impression that thermal energy flows from high to low temperature. So the second law of thermodynamics is called entropy and is defined as disorder. A better definition would be to say that energy accelerates the particles it interacts with, and that acceleration scatters matter randomly. Afterwards, universal expansion continues moving the scattered matter in all directions. Actually, entropy or disorder may not be a bad definition for the second law of thermodynamics. Time and entropy seem to have a direction. They appear to move forward. Lately, I've read reports of the idea that time results from entropy. Well, the link on the right side is a presentation on time, what it is, and how it's created. The presentation posits that time is a momentary field created by universal expansion alongside space. As a visualization, imagine an electron being created in front of you. As the electron expands from zero to its full size, a magnetic field forms around it. When the electron reaches its mature size, it stops expanding and magnetic field collapses. Time follows the same pattern. As a pixel of space is created, a time field appears around it. After the pixel reaches full size, the time field disappears. And although time and entropy share a common cosmological foundation, which is universal expansion, they are two different concepts with different functions. Like everything else, entropy depends on time, but time is independent of the second law of thermodynamics. Experience dictates that whenever energy and matter collide, entropy increases. A high velocity bullet crashing into a glass creates a great deal of entropy in the room holding the glass. But based on this presentation, entropy depends not just on the amount of energy and matter in the system, it also depends on universal expansion. Astronomers tell us that universal expansion carries galaxies past the visible universe edge, the particles horizon. Since energy cannot be contained, it too must move past the visible universe edge. This process slowly drains whatever matter and energy exists in the visible universe. So, if the density of matter and energy in the visible universe decreases, entropy must also decrease. And when all matter and energy have crossed the visible universe's edge, the entropy of the visible universe must drop to zero. So maybe the entropy of a room increases when a glass is shattered, but universe wide, entropy is decreasing. Scientists have looked at this problem from a different perspective. There's an assumption that the universe will end in a heat death called the big freeze, and black holes could be the storers of entropy. In this case, entropy will stop increasing but not decrease. Another solution to the decreasing entropy problem could be found in what's called the de Sitter space, a solution to relativity that involves a universe with no matter or energy, and entropy being a function of fields, not matter. But that requires a cosmological constant, which is dependent on dark energy for its acceleration. And my definition of energy requires the universe to expand at a speed of light, not accelerating. So, in summary, the second law of thermodynamics is usually called entropy or disorder, although a better statement to say energy cannot be contained. Entropy results when energy collides with and is absorbed by matter, which accelerates matter along any of the three dimensions. After the collision, universal expansion keeps matter moving at whatever velocity energy imparted to it. As for time, it is independent of entropy, but entropy depends on time. And because universal expansion is constantly carrying matter and energy outside the visible universe, the entropy of a universe must decrease and eventually it must disappear unless it's stored in black holes or universal fields.